Okay, Calc PC, I'm here to teach you all about your next lesson, got a last lesson in this chapter actually. What we're going to learn about today is called the alternating error bound. Now the feedback I got yesterday was people loved Lagrange error bound. This is very easy, very straightforward. Asked if we could have even more error bounds. Okay, and the alternating error bound is actually easier. So this is what I prefer. So here's the general flow of it. If you have an alternating series. So we're going to put 3 kind of bullet points here. So if you have an alternating series and the limit n goes to infinity of all the terms is equal to 0, and the absolute value of the terms is decreasing. So, by the way, these should look familiar because these are the same 3 that we learned about. This just means the series converges. So if you have an alternating series that converges. What this says is the maximum error between a partial sum, so a partial sum is just like the first n terms or whatever, and the infinite sum is equal to the absolute value of the next term in the series. And that should actually warm your heart, because when we think about the next term, that's just what the Lagrange error bound was looking at too, right? It was looking at the n plus 1th term after you use an nth degree estimate. Okay, so let's take a look at a couple examples. I'm going to show you one not even having to do with Taylor-Maclaurin series, then we'll do some Taylor series stuff. Okay, so say I ask, just how far is the sum from 1 to 4 of -1 to the n over n squared? How far is that away from the actual infinite sum from 1 to infinity of -1 to the n divided by n squared? Okay, now when you're writing these answers up, and you often do see this on the FRQ, you want to list those 3 conditions first. So what you'll say is, okay, so this series, and you don't even need to verify, you just kind of list this series alternates. The absolute value of the terms decrease, and the limit is equal to 0. So that means that my error is the absolute value of the next term in the series. And the next term would just be, if I went 1 term further, what would it be? So in this case, I went to 4, so my next term would be 5. So I'm going to plug in n equals 5. So it's the absolute value of -1 to the 5th over 5 squared, which is 1/25. Okay. So what that's telling you is this estimation of just looking at the first 4 terms is off by only at most 1/25 from the real actual sum of the series. Okay. You might be wondering why this happens, and this actually goes back to that example we had a while ago, that if you have so this series, by the way, is like saying, okay, we have a -1, and then after we do the -1, we do plus 1/4, and then we go back 1/9, and then we go plus 1/16. So the idea is after we kind of go forward here, once we say plus 1/4, I'm never going to go that far back again. Once I go 1/9, I'm never going to go that far back again. And I'm kind of like limiting myself every single time, just getting closer and closer as I add the terms. Anyway, you don't need to know that. That's just kind of like why this works. Because as these terms get smaller and smaller and keep alternating, like your sum is here, and then here, and then here, and then here, it's just kind of getting like pigeonholed in from both sides where it's approaching one value. Okay, so let's go ahead and look at some other examples here. So suppose we tell you, and you really need to know this, of course, the Maclaurin series for cosine of x is this. Is cosine of x equals 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. Okay, so if I ask you for a 4th degree estimate of cosine of 1, a 4th degree estimate of cosine 1, so that's saying x equals 1. So if I just looked at the terms up to x to the 4th degree, of course, means x to the 4th power. So that would be cosine of 1 is approximately 1 minus 1 over 2 factorial plus 1 over 4 factorial. So I guess we could do, that's like 1 minus a half plus 1/24. So that would be 13/24. So the question we would want to ask is, how far is this from, or what is the error from the real cosine of 1? So how far from the real cosine of 1? Okay, and that's what the error bound lets us do. Okay, so this series, and again, this series is an alternating series. The terms go to 0, and the terms decrease. And those are just those same three conditions we always just want to kind of vomit out each time. So we just look at the next term. And again, I just mean literally the next term in the series, this sucker right here. So the error is the absolute value of the next term. So it's the absolute value of negative, okay, we're plugging in x equals 1. So the error is 1 to the 6 over 6 factorial, which indeed is 1 over 6 factorial, also known as 1 over 720. Which is very close. So it tells you this is actually a really close estimate of cosine of 1. And this is, again, the worst case scenario. So we are within we're within 1/720th of the real value of cosine. Okay, so that's the example. Let me show you one more. Here's an old AP question from a couple years ago, although this has actually been on the AP test the last couple years, so we'll do those problems in the next couple weeks. Okay, so let's say f of x is equal to e to the negative x. The question asks to use a Maclaurin series. Use a Maclaurin series to find p sub 2 of x, which is, as usual, our second degree polynomial. And then we're going to do that, and we're going to estimate f of 0.1. And then we're going to show that this error, this absolute value of f of 0.1 minus p sub 2 of 0.1 is smaller than 1 over 5,000. Okay, so we saw this kind of notation. We're not like plugging into this. That's not what you're doing. This is the difference between the real value minus the estimate value. So this is your error. So what you're going to do is you're going to find the error, and you're going to show that that error is smaller than 1 over 5,000. Okay, so first off, let's go ahead and write this series out. So e to the x, again, we're not a bad student. We have this memorized, so we know this is what it looks like. So if we plug in e to the negative x, so that's 1 minus x. Here the negative x squared becomes a positive, okay? And then, I should put dot, 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 and then minus x cubed over 3 factorial. Okay, so now the problem said use p sub 2 of x to estimate f of 0.1. So we're looking at the first one. So that means that f of 0.1 is approximately 1, that's an approximate sign, 1 minus 0.1 plus 0.1 squared over 2. Okay, so this series, again, we want to list the three conditions. The series alternates, the absolute value of the terms decrease, and the limit is 0. They're going to look for you to write all three of those those qualities out on a free response. So that means that the error is the absolute value of the next term in the series. Okay, so we go back to the next term of the series. That would be the x cubed over 3 term. So it's going to be the absolute value of negative 0.1 cubed divided by 3 factorial. Okay, so let's write that as a fraction. So that's 1/10 cubed divided by 6, which is 1 over 1,000 over 6, also known as 1 over 6,000. Okay, now the problem asked me to show that error was smaller than 1 over 5,000. This is. If you don't get something smaller than 1 over 5,000, you screwed up. And we know that 1 over 6,000 is actually smaller than 1 over 5,000. So, yay, we're done. Okay, so that's the gist of these problems, really. The key is just look at the next term. That's it. And literally just look at the next term, plug in whatever x value if it's a Taylor series, but just look at the next term. You might be wondering, like, when to use this versus Lagrange. So here, really, there's only one thing. Does it alternate? If so, use this. If not, use Lagrange. Sometimes, obviously, I'll say use Lagrange airbound, but if you have an alternating series, if so, use the alternating error because it's way easier? And the answer is if not, then you go with our old buddy Lagrange from yesterday. Okay, that's the lesson. Good luck on the homework. I'll have office hours tomorrow early in the afternoon if you have questions, and thanks for watching.